Welcome to the lesson on colligative properties for Regents chemistry, following intermolecular forces in chemical bonding. All right, so first of all, what is a colligative property? These are properties that depend on the number of dissolved particles in a solution. So these are properties of solutions, and they describe how the properties of a solvent changes once a solute is dissolved in that solvent. All right, and something that's very important is that these properties don't depend on the identity of the solute. So, it doesn't matter if it's a salt, if it's an electrolyte, a non-electrolyte, it doesn't matter. All that matters are the number of particles that become a part of the solution. So what's really important is what's called the Van Hoff factor. Now, this isn't on the Regents exam, but it's something that's good to think about, and if you go on in chemistry, you'll see this variable. So this term I gives you the number of moles that the particle kind of breaks apart into in solution. If you have a non-electrolyte, this number is always going to be 1, but if you have something that dissolves, if something undergoes dissolution, like ionic salts do, then this number will be basically the number of pieces, and for an ionic compound, the number of ions. So if you look at this example here, I show you two ionic compounds, sodium chloride and calcium chloride. As you can see, sodium chloride's chemical formula is NaCl, so it's going to break apart into 2 ions, and its Van Hoff factor is 2, whereas calcium chloride's chemical formula is CaCl2. As you can see, 1 calcium with 2 chlorine atoms. And for this compound, the Van Hoff factor would be 3. So for colligative properties, even if I were to add the same amount of these 2 salts, so let's say that I were to add a mole of sodium chloride and a mole of calcium chloride, the calcium chloride would cause more aggressive colligative properties to skew. So we're going to see what those colligative properties are, but calcium chloride would have a greater effect on those properties than sodium chloride would. Alrighty. So dissolving a substance changes that solvent's properties. Why is this? The reason is because the intermolecular forces get interrupted once you add the solute particles. And as we learned, intermolecular forces are key in determining physical properties, such as these here. So when you add a solute to a solvent, these 4 properties will change. So vapor pressure is going to decrease, boiling point will increase, freezing point will decrease, and osmotic pressure will increase. All right, so let's first look at the process of dissolution. What's actually happening here? So as you can see, when water is just water, you have hydrogen bonding present. These are the intermolecular forces between water molecules. As you know, hydrogen bonds are very strong dipole-dipole attractions, where you still have the partially negative oxygen attracted to the partially positive hydrogen, so these are still electrostatic attractions here. When you have a salt dissolve, for example, so let's look at sodium chloride. What happens is the water is going to form new intermolecular forces with those ions. As you can see here, this is called the shell of hydration. And what happens is the water molecules are going to surround the ion in such a way as to produce favorable electrostatic attractions. So the positive sodium ion is going to be surrounded by the partially negative oxygens of water, and the negative chlorine ion is going to be surrounded by the partially positive hydrogens of water. So this is how, dissolving a salt can interrupt the intermolecular forces. The first thing we're going to look at is freezing point depression. So when you dissolve a salt, the freezing point of the solvent is going to decrease. And this is the relationship here. So as the amount of solute increases, the freezing point is going to decrease. All right. And here's the formula. Delta T, the change in temperature, is going to equal Kf. This is the freezing point constant. Okay, so this is a constant for any material, times m, this is molality, times I, the Van Hoff factor. This is not an equation that you need to know for this exam. I just wanted you to see how the change in temperature varies directly with basically the amount of solute present. Why is this? All right, so let's think about what happens when something freezes. As we know, solid structures are the highest organized phase of matter. All right, so these have the strongest intermolecular forces. It's a rigid structure. So the molecules have to cluster and kind of crystallize. Okay, this means that they have to, be close to each other and attracted to each other. When a solute is dissolved in the solvent, basically those solute particles get in the way of the solvent and make it harder for that solvent to freeze. Okay, so I want to show you this simulation, and I'm going to rerun it here. So what you have, this is a really cool simulation by CK through 12, and you can access it anytime, it's free. And what it does is it allows you to see the effect of not only the type of salt, but also the amount of salt on the freezing point of water. So we're looking at freezing point depression here. And again, comparing sodium chloride versus calcium chloride, this is that Van Hoff factor that we were talking about. So the effect that the number of ions will have on the freezing point, right? And also the amount of salt. Okay, so as we said, as the amount of solute particles, no matter what they are, right, as the amount of different particles increases, the freezing point is going to get lower and lower. Okay, so to optimize these conditions, basically I want to release as many ions into solution as possible. So that would be calcium chloride, 3 versus 2. And I want to have the highest amount of salt, so 3 moles is the highest I can put in. So let's look at this. Now what we're starting off with is rigid ice. And as you can see, these are the water molecules, the red oxygen, the white hydrogens. They have a solid structure, crystal structure. As you add this calcium chloride, the ions are going to dissociate and break apart. So as you can see, the solute is disrupting the ice and turning it back into a liquid. So now we have salt water here at 0 degrees. You've melted all of the ice. And as you continue to freeze this, right, as the temperature continues to drop, you can see that you still have salt water present. All right, and eventually you will drive enough energy off of the solution where you will start to see the water freeze up again, right? So you're starting to see that crystal rigid structure form and the salt fall down to the bottom. All right, but as you can see, that had a really big effect on the freezing point. So negative 16 degrees Celsius, that is quite the effect. So this is why we put salt on icy roads. It's because you want to disrupt those intermolecular forces and basically make it harder for that solvent to freeze up. Okay. The next one I want to talk to you about is vapor pressure. As we know, vapor pressure is the pressure that a liquid exerts on the surface. And here is the relationship. So as the amount of solute dissolved increases, the vapor pressure on the solvent decreases. All right, and this is the same relationship we saw when we learned about intermolecular forces. All right, now let's look. Basically what that means is that it becomes more difficult for the solvent to escape to the gas phase. All right, why is this? This is actually explained by Raoult's law. So basically what happens is when you think about the surface of a liquid, right, there is a surface area that it's exposed to the gas, right, to the atmosphere. If you have a solute dissolved in a liquid, basically you're decreasing the fraction of surface that is solvent particles that could escape, right? So that's what this is saying here. The solute is going to decrease the amount of solvent per unit volume. So basically it's kind of like diluting the solvent at the surface. So less solvent particles are present to escape to the gas phase, which is going to lower your vapor pressure. You are not responsible for knowing Raoult's law. This is just showing you how the proportion, this is mole fraction here, how the proportion of solvent to solution is going to have an effect on the vapor pressure. So it's really a proportionality thing. How much surface is solvent, right? It's only a fraction, so you're only going to have a fraction of the vapor pressure. Now, what does that mean? That also means that you're going to be raising boiling point, because we know that boiling point is directly related to vapor pressure. Boiling is when vapor pressure equals atmospheric pressure. So if adding a solute is going to decrease the vapor pressure at any given temperature, that means that your boiling point is going to increase. All right? So as the amount of solute dissolved in a solution increases, the boiling point of that solvent is also going to increase. And as you can see, this equation looks very similar to the freezing point depression, where the change in temperature equals that constant for any material times molality times the Van Hoff factor. Again, as you can see, temperature varies directly with the amount of solute present. Okay, so again, what happens during boiling, you have to break those intermolecular forces between all the solute and now the solvent and solute particles, right, to escape to the gas phase. And again, because vapor pressure is lowered, that means that your boiling point is going to increase, okay? Because if it's harder for your molecules to escape to the gas phase, that means that you need to give them more energy to do so. Okay, lastly, we need to discuss osmotic pressure. So you may not have discussed osmosis since living environment. So just a quick review of what this is. Osmosis is a special case of diffusion where water is going to travel against a concentration gradient. So if you look at this image down here, you know, osmosis is kind of movement of water through a semi-permeable membrane. So in this kind of demonstration, you have a pure solvent, so let's say water on one side, and you have a solution like salt water on another side. What's going to happen is just naturally water is going to travel through the semi-permeable membrane, right? If salt can't pass through, right? If the solute is unable to pass, then water will travel from the lower concentration to the higher concentration of salt. And the reason for that is it's going to try to reestablish an equilibrium of concentration. So water will move to try to create equal concentrations on both sides of the membrane. All right, so in this example, as you can see here, let's say that you have solvent and then the solution. Water will travel from the left to the right side and to try to make those concentrations equal. And as you can see, the water level could actually be different and will be. Osmotic pressure is the equal but opposite pressure needed to resist the water flow. So as you can see here, osmotic pressure would be the pressure applied to the solution side to keep the water from flowing, right? So the osmotic pressure can be measured as the distance that water would rise, basically, in a calibrated tube, okay? And a lot of times you see this through cell membranes and things like this, hypertonic, hypotonic solutions, but it is a colligative property. So as you can see here, osmotic pressure varies directly with the amount of solute present. So pi is osmotic pressure is equal to molarity times the gas constant times temperature in Kelvin times the Van Hoff factor. So as the number of solute particles increases, the osmotic pressure is going to increase. And that's it for colligative properties. If you have a question, you can drop it in the comments or email me. Have a good one.